In this video, I'm going to talk about relative extrema. Now to do that, I'm going to have to define a couple other terms first. So we're going to look at what it means for a function to be increasing, decreasing, and constant. It's a relatively simple term, so we'll start with increasing. A function is increasing if the y values increase as the x values increase. A function is decreasing if the y values decrease as the x values increase. Constant is a function's constant if the y values stay the same as the x values increase. So notice all three cases we're talking about as the x values increase. All that's saying is reading from left to right. That's what we're looking at. Reading from left to right, what are the y's doing? Are they going up? Are they going down? Are they staying constant? So some examples of an increasing function. This line going up, could be a curve going up. It doesn't have to be, consistent rate of increase as long as it's constantly going up. So it could be going up a little bit, then curve more up, then slow down, then go up again. So again, not a consistent rate going up, but the fact that it's going up that entire time, it never levels off, it never turns back on itself. Decreasing, going from left to right, we see that it's going down. Again, it could be a line, a curve, it could be some sort of wobbly shape where it's going down. As long as it never levels off or turns back upwards. And constant, really only one picture I can give you for this, horizontal line, or a portion of a horizontal line too. It doesn't have to be that it's, goes on forever and ever. It could be some sort of segment of any of these. We're going to take examples of this as we go along, but I wanted to find a couple other terms first. Relative maximums and relative minimums. A relative maximum is a point whose y value is larger than the y values of points immediately to the left and to the right of the relative maximum. Relative minimum is a point whose y value is smaller than the y values of points immediately to the left and the right of that relative minimum. Together, these two things are called extrema. So remember I started off by saying we're going to talk about extrema. Extrema refer to the maxima and minima together. Maxima, plural of maximums, minima, plural of minimums. But extreme are just talking about both these things, referring them all kind of as a group, referring to all of them. We are going to be talking about the relatives. Relatives also called locals. There is another type of max or min called an absolute or global, and that's different. We're not going to really get into that in this video. That is down the road, especially talk about these a lot more in calculus, but we're just going to focus on the relatives for right now. Now, why did I talk about the increasing, decreasing stuff first? Well, that's going to play a very valuable role in these maxes and mins. So a maximum is going to occur at one of two places. One place where a function transitions from increasing to decreasing. And secondly, potentially endpoints that are higher than the graph around. So endpoints can be extrema, and then these turning points as well. In the case of the relative minima, these are points where a function transitions from decreasing to increasing. And again, these could be endpoints, but this time that are lower than the graph around it. So to give you a couple of examples of each, I'll start with the relative maxima. Function where it transitions from increasing to decreasing. So function's going from up to down. That point right there has to be an absolute max. It could also just be the endpoint. So think about this point right here. That point right there is larger than the stuff around it. Relative minima, where it's transitioning from decreasing to increasing, or an endpoint that is smaller than the stuff around it. So I don't really care what those other ends are doing, just as an example. Let's take a look at a graph and we'll determine some of these elements. So this graph's going to start at the point -2, -1. Go up and it's going to turn at the point 0, 1, the y-intercept. Go back down and it's going to turn at 1, 2. And it's going to go up and up from there. So each of these little ticks, just so I don't get too messy, each of these ticks is represented by 1. So let's start by defining let's do the domain range for starters, just to practice those skills. So the domain, remember the domain, the values that x takes. We can see the x goes from -2 to infinity. -2 in a bracket to infinity because the -2 is included. Our range, the lowest this gets, is at -1, and these are meant to be the same height. I just have an imprecise graph here, but these are meant to be the same height. They go down to -1. So from -1 to infinity. Next, I'm going to define the increasing, abbreviate, decreasing, and constant regions. Now, if I want to talk about where this function is increasing, it's not just at one number, right? It's this whole range from here to here. It turns, it's meant to turn at the y-axis. From here to here, it's going up the entire time. So we're going to have to use our interval notation to define this increasing space as well. Notice the function starts increasing at -2, and it finishes increasing on this stretch at 0. So from -2 to 0. With domain and range, we would include these with brackets because they were included points, and they're still included points. But for increasing, decreasing, and constant, we're always going to use parentheses. Always. This is an extremely common error putting them in brackets. For increasing, decreasing, constant, we will always use parentheses. Now, why is that? It looks like -2 is included, 0 is included. That is true. They're there in the graph. We're not talking about what's there and what's not. We're talking about how the graph is moving. If I were to put -2 to 0, what I'm saying then is if I look at the point -2, -1, that point is increasing. That point's not increasing. That point's not moving. It's a point. It's not until I see the movement between 2 points that I actually see that movement. We can't see movement at a single point. That's why we never include these with brackets. That'd be like me saying go out to the highway and take a picture. If you look at that picture, it doesn't move. There's no motion there. Now, are the cars moving when you're standing at the side of the highway? Yes, because time is passing there. We're seeing motion between points. But in that instant time, that picture is not moving. We would have to take a video, a time lapse, to be able to see the motion of that car. Now, this is not the only interval for which the function is increasing. It's also increasing from here to here. So that starts at 2, and that goes on to infinity. So from 2 to infinity, it is also increasing. Notice I use parentheses again because we can only see motion between points. It's decreasing on the space between that. So from 0 to 2, the function is decreasing. And there's no regions, none, in which the function is constant. It never stays the same. Notice that this increasing, decreasing constant space should span the entire domain. The domain is all the x values that exist. Well, other than the points at which it transitions or it turns, it has to be doing one of those 3 things. It has to be increasing, decreasing, or constant. So we go from -2 to 0, from 0 to 2, and 2 to infinity. Notice we're going from -2 to infinity. The last thing I want to do is I want to define the relative extrema. So let's see if we have any relative maximums. I might just define them as points at first. So I'm looking for endpoints or points at which the function transitions from increasing to decreasing. So let's take that second one first. Are there any places where it transitions from increasing to decreasing? Well, yes, it goes from increasing to decreasing right here at the point 0, 2. There are no other points at which it transitions from increasing to decreasing. This increasing continues to increase forever and ever. So that's the only one that occurs through the transition. If we look at endpoints, there's only one endpoint. That endpoint is not higher than the stuff around it. It is not larger than the stuff in its neighborhood. So this point 0, 2 is the only relative maximum. Now, is that maximum the absolute highest number on the graph? Clearly not. This thing continues to go on forever and ever. This point is definitely higher than that maximum. We can see that. But that's not what we're saying here. We're saying, is it highest in its little community, in its little neighborhood? A lot of times I'll describe these by using the idea of a neighborhood. If you think about the richest person on your street, you can have a richest person on your street. It doesn't mean that they're the richest person in the world. That is whoever is the richest person of the day. Elon Musk, Bill Gates, Jeff Bezos, whoever it is that particular day. They swap around all the time. Whoever is the richest person in the world would clearly be the richest person in their street, but we're not talking about the world. We're not talking about that absolute richest person. We're not talking about the absolute largest thing. All we're saying is, in its little community, is it the largest? And in the case of this 0, 2, yes, that point is larger than any of the points left to right of it. And we can make that community as small as we need to. So we could look at, again, the state of North Carolina. Are you the richest in the state of North Carolina? Well, no, but maybe if we look at your city, maybe. Well, if you're still not, then can we look at your street? Is there a smallest territory to the left and the right of you that we can find? Now, if even to the left of you, there's somebody richer, if they're immediately to the left, then that's not going to win out. That is not a maximum. Next, I want to look at relative minima. Here, if we start with the idea of where it goes from decreasing to increasing, we see that we have one of those points right here at 2, 1. If we look for any endpoints, there is an endpoint too where this is the lowest in its little area, and that occurs at negative 2, 1. So negative 2, 1 and 2, 1. Sorry for the jump. And so we have two relative minima in this case. Now, they actually have the same minimum value. The minimum value is 1. It didn't matter that it repeated. Again, it could have had lower values across the function, but in its little neighborhood, if it's the lowest, that's good enough. Now, there's another way we could define these. I've done it as points in this case, but we could also define in terms of words. So we could say, in the first case, the relative maximum is 2. And the x value describes the where it occurs, which occurs at 0. The relative minimum is 1, which occurs at 2. Excuse me, I got that wrong. The relative minimum is 1. It is the y value, not the x value, which occurs at 2 and negative 2. The value is always the y coordinate. The y is always the value, or how much the function actually is. The x is the where it occurs. So if we're talking about the min or the max value, that is talking about the y. The max value is 2, the min value is 1. Where those occur, those are the x's. That is much in the same way we describe the increasing, decreasing constant regions. Notice we use the x's to describe them. How are we determining if a function is increasing or decreasing? We're looking to see what are its y values doing. Are the y values going up? Are they going down? But how do we describe when that occurs? We're using those x values to describe when that occurs. So that's why we use the x values here. Let's look at one more example. So again, each tick mark representing just one. If we were to define all the same elements of this one, let's talk about domain. Domain goes from negative infinity to infinity. The range goes from negative infinity to 1. That's the old stuff. The increasing regions, we can see it starts increasing right away. Don't let your eyes follow the arrows. If you just let your eye follow the arrow down, you would be saying, hey, this is going down. It's not how we read. We always read from left to right. So it's not going down. This is actually going up as we go from left to right. So always make sure that you're reading from left to right. This is going up even though the arrow looks like it's pointing downwards. That just indicates continuation. So from negative infinity to 0, the function is increasing. The function is decreasing from 1 to infinity. Notice I'm using parentheses again because I will always use parentheses on these. And finally it's constant in that in-between space, so from 0 to 1. From here to here, the function remains constant. We covered the whole domain, from negative infinity to 0, 0 to 1, and then 1 to infinity. We've covered the entire domain. Relative extrema, maxes and mins, there are actually none in this case. Remember the definition, it has to be the largest in its little community. If we look at, say, this point, we're going from increasing to constant. Well, this value of 1 is not the highest in its neighborhood. If we go immediately to the right, it is tied. It's not the largest. It's not a relative extrema. If we look at relative minimums, there are none, right? There is no smallest value in any neighborhood. Again, this value of 1 is tied with things on either side, so it's not the smallest in its neighborhood. It doesn't matter that the arrow is going down. I don't really care that there's no smallest value ever. I care about in any given neighborhood, there is no smallest, so there are no extrema. We need to be looking for endpoints and where it's transitioning from increasing to decreasing, from decreasing to increasing. That never occurred. We transitioned from increasing to constant to decreasing. So we never had any relative extrema.